Hello, welcome to the second video in my YouTube series on neural nets and Connect 4. What I talked about in the first video was how the neural nets were actually first trained to play Connect 4 by using a minimax algorithm to generate output move data, and then mapping the neural nets from those board inputs that were used for the minimax algorithm to the moves output by the minimax. What I'm going to talk about today is self-play learning that was implemented in the project. So there are two main components to that. There's the Monte Carlo tree search and the integration of neural nets into the Monte Carlo tree search, and then the generation of data using this kind of new neural net Monte Carlo tree search to generate data to train neural nets on, similar in the way to how we train them to emulate the minimax algorithm, and then using those new and improved neural nets to create a better Monte Carlo tree search, and kind of comparing the results and assigning the champion according to those results, and just continuously doing that again and again and again, and getting better and better performing neural nets. So what I want to start with is just talking about the Monte Carlo tree structure actually without the neural nets, and then we'll talk about the integration of the neural nets, and then finally get to all that self-play stuff. But what I want to do to start it off at the very start is just talk about how it's different from the minimax algorithm. So the minimax algorithm I went through last episode. You have your heuristic, whose job it is to take a game state and then assign a score to it. The score is supposed to be an indication of whether that game state is favorable or not for the current player. And you also have your depth, and your depth is like it basically represents how far ahead the minimax algorithm is looking. So that is usually chosen according to a time constraint, how long you're willing to wait, or depending on like what application you have, maybe you do have hard time constraints. Basically, because these Connect 4, if all the moves are available, you have 7 moves, so it's growing kind of exponentially throughout the tree. From every child, you'll have 7 moves available. So even, that's a relatively low branching factor for most games. Something like chess or Go are both, a different order of magnitude higher, but it's still high enough that it grows very, very quickly. So if you don't have like a dedicated kind of like AI kind of server set up, then you're gonna be waiting for even, small depths. Like for me, it really starts kind of getting longer around like 5 or 6 moves ahead in the minimax tree. But basically, the way the minimax function works, just to give a brief overview, is it goes down to the depth that you have assigned, and it starts scoring those boards. And it is basically the whole minimax, where it actually gets its name from, is it assumes that the current player is going to choose the best board for them according to the minimax algorithm. So it's called the minimax because you assume that the opponent is going to choose the minimum score, and then you're going to choose, and then the current player is going to choose the maximum score. But basically, it kind of propagates those values that it gets from scoring back up. According to that logic, and eventually they get all the way back up to the root, and the root gets a score, and it also gets that kind of like path, like here's how you guarantee yourself the highest score from this position according to your heuristic and your depth chosen. That's kind of a quick explanation of how the minimax algorithm works. The Monte Carlo tree search works quite differently, even though the structure is pretty much identical, in the sense that so both of the structures will have the current state as the root, and then from the root, the children that get created are all of the children that are available from that root, meaning that these are the game states that can be accessed via legal move from that root. So that part of it is the same. The way that the tree is actually generated is quite different. So the minimax tree kind of uses it's closer to a depth first search, in that it goes like all the way down one branch, and then it'll do all the sub branches, and it kind of works like that. So, but a consequence of that is that you can get drastic value swings towards the end. So you could have, you could go through all of the branches except for the last one, and on the last one, suddenly you discover that your situation is really different than how you thought it was before. The Monte Carlo tree uses what's called like a best first search, in that so the Monte Carlo tree is designed to kind of pursue the most promising options, but also balance that with exploring according to configurable variables that you set, like according to your application and needs. So the way that the pure Monte Carlo tree search works is that it will so first off, you start with just your root node, and basically with the Monte Carlo tree, you have a set amount of iterations that you want to take place, and with each iteration, you get better and better information. The first iteration would be to expand the root node, so you have all of the children from there available, and without neural nets, the traditional technique is to just use random rollouts, is what they're called, when you just you randomly play out the game from that state. So if you kind of imagine if you play out a certain game state with random moves, a very large amount of times, you'll get an idea of like how good that game state is. From that, or like how favorable, like you kind of get an idea of the percent chance of winning from that position. So that's the logic that follows, but you only do a rollout from a game state once when it gets expanded, and then on the next cycle you go down and you expand a new node. So you choose which node to expand based on kind of a formula which that's the formula that I mentioned earlier. It kind of pursues the most promising scenarios, but it's also balanced by saying if a node hasn't been explored very much, well, we should look at that and see if there's anything good there. And if we find that it is really bad, then now we know. So like I said, the way that's traditionally done is with the rollouts, but the way that we're using this with neural nets, we're not doing rollouts. We're using neural nets, and they're actually what are responsible for scoring the boards, kind of in the same idea how a minimax has a heuristic that gives a board a score. We're using neural nets to look at a board and give that board a likelihood of winning. And there's also a different policy neural network that's used from the parent node, which gives us the probability of a certain move being played from that position. Those values are kind of used in the same formula and combined, and that's what gives us our final score. To actually compare that node with the other ones on its level. That's all I want to say as a brief overview. I think that we can start looking at some code now. So we're going to be looking at two files mainly. There's my MC file, which stands for Monte Carlo, and then there's my self-play file here, which contains kind of like all the self-play functions. I'm just going to go quickly through the Monte Carlo kind of tree structure and the three important functions. So those iterations that I mentioned earlier, there's kind of each iteration basically consists of 3 steps. There is the recursion, so select recursion step, whatever you want to call it, where it actually goes through the existing tree and finds the node that it's going to expand. Then there's a process of expanding that node and scoring all of the new nodes that are created, and then there's the back propagation, in which those scores are pushed back up through the tree, and the parent's node scores are adjusted according to the scores of the newly expanded nodes. I'm actually like the minimax tree. There's also nodes. This function's pretty much the same. We have some variables here. There's the denominator. The denominator is used to track how many times the node has been explored, which is an important value for, like I said earlier, the formula that's used in the recursion select. One of the important variables is the denominator, how much that node has been explored before. There is the neural net probability. That's what this stands for. That is the value that's assigned from the parent node. So we have a neural net that analyzes the parent node, and it gives a prediction of which move will be played from that scenario. There's also this NN value, so that's the one that looks at the current board and gives a value between 0 and 1 on like how strong that board is for the current player. And then there's some stuff here to keep track of the state of the node. So we see if it's expanded or not. We see if the board is completed or done. So that means like if there's a draw or a win. And here there's the flag that if it is a win or not. Let's look at the select recursion function first. You might be wondering why I have quite a few functions here. I actually wrote this, at first I wrote the tree without the neural nets and integrated them later, so that's why there's kind of clone functions here. There's select rec, there's NN select rec, and then there's select rec, same thing with expand and back prop. That just means that each of these 3 functions are using neural nets, whereas these ones were using like the traditional rollout method. So let's just take a quick look through the select recursion function. The first thing it checks is if the board is completed, and that's when it calls the back propagation function, which we'll work out later, but it's actually using hard-coded values, so you can see it's passing a 1 if it is a win, meaning that it's passing a, so like I said, the boards can be scored between 0 and 1. So if it's passing back a 1, if it is a win. If it's not a win, it's passing back 0.5, because that means it must be a draw. And then returns that node. So this is kind of the most common one that we'll see here if the node has already been expanded. So it creates this value list. The value list is going to be the list of the values that we're comparing to each other. The maximum value is going to be the one that we're going to actually pursue. So for child in node.children, so for each child of that node, and then I'm using this formula now. I'm going to take out this later. This was a formula that I've replaced, but this is the formula that's being used here to populate the val list. So we have val list.append. So the neural net value, this is the one that's assigned by the value neural nets, the value between 0 and 1 of the probability of a win or not, basically, over the child denominator. This is an exploration constant. Basically, the higher this is, the more likely your algorithm is to choose a node that hasn't been explored. It kind of gives a more even exploration rather than like greedily pursuing the most promising move. This is our probability value that was generated from our policy neural net, and then we have here just an expression of the so the denominator of the root, the amount of iterations in total that have been performed on the tree, over the amount of times that the child has been explored. So as you can see, like, that value will be higher if the tree has been explored a lot and the child has been explored very little. So that kind of goes in hand with like this whole term here. Basically, it's two terms. You have this term, which is like how valuable the node is. This is the average value of the node. And then you have this one, which is kind of a function of the likelihood of it being played initially, and then it gets larger as the tree is explored and gets smaller as that specific node is explored. So after we've completed our entire val list for each of the children, then we call a function recursively. Because this node is expanded and it has children, we can't expand it again. We're going to be calling the function recursively on it. This expression here just finds the maximum node in the val list and expands on that. And then, so if neither of those are true, then that means that, so the board isn't completed and the node hasn't been expanded, then we do expand the node. So that's the next function that we're going to look at. In the node expansion, so first thing first, we're generating those NN prob values. So we have a move prob, which is going to be a list of values. And then we're looking, so for each legal move, first we're creating the node, so we're initializing it with basically the board that it needs. Here we're creating the child node, and we're adding that to, and we're going to be appending that to a list later. Yeah, parent node, children, append, child node. So here we're checking some stuff that we need to know about the board. I didn't rely on the neural nets to tell me if a board was a winning board or not. I'm using like the engine logic in Connect 4. So we do a check win, and we're hard coding those values. If it is a win, and we're saying the board's completed. If it's a draw, we're assigning 0.5. If it is neither of those, then that means that the board is still ongoing, and this is where we use our neural net. So we have our value neural net. So this is our val model. Here's our Paul model earlier. I probably should have pointed that out. And it's predicting based off this sort of boards to inputs function. So like we're not using the cells that are used in the engine. We're using those like vector inputs. And so it's been trained at this point to kind of score boards, and it generates its list values, and that's how the NL value, the neural net value, gets assigned. For each node, we're appending the children, and we backpropagate. So every time that a new node is created, you're going to be backpropagating the value of that node through the tree. So you always increase. So the way backpropagation works is you just kind of go to the parent of that node and you adjust its values according to what you had below, and then it goes to its parent, and you do that all the way through the root. The one thing that is kind of strange about it is like you only adjust the NN value if that node kind of belongs to the same player who made this turn. So just to make that clear, like if I'm red right now and I've made this turn, then I'm not going to be changing the NN value of the node right above me. Even though you do change the denominator, but it's every other node on the tree, like every other level that you're going to be adjusting that value of. So that's what this expression ensures. Because, and the reason that we're doing that, you want this value. So we're not worried about like our opponent's boards. We're worried about our boards, how these boards look to us. So because our opponent's boards are going to be their likelihood of winning, these are going to be this is going to be our likelihood of winning. So anyway, that's why you use that. We're only doing it for our boards. The denominator is always incremented by 1, and then here we have we're calling this recursively. If this Cur node has a parent, then it's going to back prop and do the same thing. Those are the important functions in the Monte Carlo tree. There's a couple others here that are important. There's 2 different make move functions. There's an exploratory move and a make move. So this is kind of like a deterministic way of making the move. It makes the best move available. This one, it generates probabilities for all the moves, and then it can make a move according to those probabilities. So if it says we have a 50% chance of playing this move, a 10% chance of playing this move, and so on and so forth, it'll choose the moves according to those probabilities. This was important for training the neural nets because one thing that I found is the neural nets were playing the same games against each other over and over again using this function, and obviously that's not good for learning. So I switched to like a probability approach. There are ways where you can kind of control. You can kind of affect the likelihood of them choosing. Them choosing how the probability works. So basically, you want to explore the games a lot at the start, and then you can kind of zero in and start choosing the best moves later. There's a way to do that using something called temperature, in which you so let's say that we have the way that the final decision is made to make a move is how many times the node has been explored. What you start doing with the temperature stuff is so you can make a probability vector based off that. So let's say that each node has been explored. Maybe there's one node that's been explored twice as much as any other node. So if you do some exponentiation to each of those values, then the larger nodes will increase at a faster rate than the smaller ones, and you use that probability vector instead, all the way up until you're eventually choosing the highest value. And then you're getting the same output as the deterministic move chooser all the time. So that's what I wound up using in the self-play stuff. I can show that a little bit later as well. But yeah, with that, I think I want to move on to the self-play stuff and actually just start talking about the self-play process, and hopefully the whole way the Monte Carlo tree makes sense. So in the self-play process, there's this is the kind of short function here where we load our models, and then there are 3 kind of steps to the self-play process. First, we're creating a training set. So that's creating like the boards and the move pairs and the boards and the value pairs that we're actually going to be using to train our neural nets later on. Then there's the create challenger pair. So I'm saying pair here because we have that policy and value neural net. So you're creating a pair of neural nets to be used in your new model. And then there's a model showdown, which is just like a best of X. In my case, I have it set to 50 at the moment. But I used to have it at like 100. You can put it to whatever you're satisfied with, so that you're confident that you're getting the better champion. And that's where the champion is actually chosen. So let's say that my neural net wins, then hooray! Some self-learning has occurred, and but a lot of the time it will lose. I can explain why in a little bit. But first, let's look at the create training set exploration function. So the training set loads the value and policy current champions, and then it's playing against itself here. So we have a training set size. So I have each training set. It generates 100 new boards each time. So it'll create an empty board, and then it just analyzes that board, it does its recursions here. So this is the recursion function that I was talking about earlier. We have our nn select rec being called on the root, goes down through the root, expands, and does the value assignment and backpropagation. And then here's our temperature function that I was talking about earlier. So if temperature, once the temperature reaches 1, then it's moving deterministically. I actually have an if-else that's taking care of that, but also it becomes more deterministic as it gets closer to 1. The way that that's happening is I just have a rate. So at the start, the temperature is 0 and is moving the temperature is 0 and it's moving according to like the flat probability output. The probability isn't affected at all. And but as it gets higher, if we look in here, the exploratory move, this is the value that's actually getting made. We're using the term val list again, but this time instead of using the child denominators by themselves, they're getting this is the exponent operator in Python. And as you can see, as the temp, it starts off at 0, meaning that this term would be 1/1, which is 1, which means that the the exponent operation doesn't actually do anything. But as this gets closer to 1, then this value grows, and so that means that the higher probability values get higher, and the lower probability ones get lower. Okay, so the move is chosen by one of these two functions, depending on the temperature. After that, the game board, so we're saving all these boards and associating them with the probabilities. That's what's happening in this one here. This game board is a list of boards. So for each turn here, for each turn that's happening in this game, we're keeping track of the board state, keeping track of the player turn, and we're keeping track of the probabilities generated for that board state. And that's all getting saved in this game boards variable, which is in here, which is just an array. We're also tracking two other things. We're tracking has winner, so that's whether the game ended in a winner or draw, and then we have red wins. So obviously, this only gets populated if this only gets looked at if the has winner is true, and then we can say whether red or yellow won from there. So we do our check wins. We set those variables all accordingly. So if it is a win, this is actually where we're using the row num and column num that we got from here, because we're just going to be checking that coordinate on the connect 4 board. We're not checking all the coordinates. We're just checking the one that was played. So if there is a winner, then we set has wins to true. We set the red wins to the current value of the is red turn. Then we're adding to our training set. So our training set is the new boards that are getting created here. So we either load our old training set or we have our new training set here, which is just an empty list. In every case, we're going to be appending the Cur Set, which is kind of like the game, and then these little flags here that gives info on the output of the game, or on the outcome of the game. And in the case where the game is not over, then we're down here and we're toggling the is red turn. So if it was red turn, now it's yellow turn, and we're also incrementing the turn count, which is used to control the temperature. That's basically that process. Once we've played our set amount of games, which is being decided in here, usually usually it defaults to this value, the training set size, but I have some logic happening here. Just ensuring that if the training size is below a certain amount, because training on a very small sample size is usually just a waste of time, so I'm saying that you need a minimum of 400 games to actually start training a new neural net. Anyway, once it's done, all of it cycles, then it's dumping the new updated training set, and it goes on to the next function in the process, which is the challenger creation. The challenger creation, we're just loading our value champ, our value champ and our policy champ, and we're going to train them based on the data that was created during that create training set process. So we're just fitting first off we're getting our list of boards, our list of board moves, so the move probabilities for each of those boards, and then the results for each of those boards. For our policy neural network, we're training the board inputs to the board moves that were generated. And for our policy, for our value network, we're training the board. We're using the board list as the input data, and we're using the board results as the output data, and we're fitting on that. After that, we save our newly trained neural nets to our new challenger slots, overriding the old challenger slots, and then we're into the showdown. The showdown is pretty straightforward as well. So we're just going to load our value champ, our policy champ, value challenger, policy challenger, and then this is the actual showdown in here. So our showdown, basically, these are titles for them, but you can see I'm putting in the neural nets. And what they're going to do, it's going to be, and we have our showdown size here, so our showdown is like currently 100 games, and also the recursion count. The showdown takes place in a head-to-head function, which is located in here. And it looks pretty similar to the training, the function that we use to create our training sets, except it's not using the same neural nets it's not using one tree, it's creating different trees on every turn, using the champion and challenger neural nets alternatively. Other than that, it looks pretty much the same. You can even see I've got the same logic here for the whether it's making an exploratory move or whether it's making a deterministic move. Check win, and we're just kind of keeping track of how many wins a certain each player has, and once the win passes a certain threshold. So here I say if the champ wins is times the configuration win ratio. So my win ratio is currently set to 55/45. That was the ratio being used in the AlphaGo project. If you won 55% of the time, then that was sufficient to become the new challenger. And then we have the showdown size minus champ wins and minus draw count. So that's the amount of games left available to be won by the challenger. Once the champ wins, the amount of champion wins multiplied by that ratio gets larger than this number, then the challenger victory is no longer possible and we end it. Oh, but we also get, if the challenger win count divided by the ratio is greater than the amount of games left to be won by the champion, then we say, hey, challenger wins, and we end the showdown, and we pass that data back. So when that data gets passed back, this is the actual analysis. If we say that the challenger wins divided by the champion wins is greater than the ratio, challenger wins, champ wins, that's true. If champ wins. Right, this is actually a case that I got where the champions got completely shut out, so I had to put that in because it divided by 0 and gave me an error. So that's why this function looks kind of messy. But basically, we're looking at this part of it here. The challenger wins over the champion wins is greater than the win ratio. Then we have a new champion. Woo! And so here we're just saving the old champion. I have some functions in here to keep track of like the progress of the neural nets. So you can do like generation tournaments. If you call this function, for instance, then it lets you specify a model and you get kind of a tournament where the first generation will play against all subsequent generations and the second generation will play that, and you get to see the results and how effectively your neural net is actually learning. So what it's doing here is it is kind of just, it's first parsing how many existing champions there are, and then it's creating a new champion, and then our challenger value network and challenger plus network finally get saved to the new champion slot. This was something that I had just to stop the process after a certain amount of champions were created, which I'm probably going to take out at the end. That is pretty much it. That's pretty much the self-play learning process. We saw how the training data was generated, how the training data was used, and then how the performance is actually evaluated to create the new champion. I think I might do quickly, just if you're interested in seeing what the output of that actually looks like, we can do that quick. But we don't want to do a full training set, obviously, because that will take forever. So let's just do 5 actually. And I don't know, what else here do I need? Yes, just take a look here. Okay, so bear with me a moment. This is the function that I have that kind of just calls this auto self-play function. So it's going to ask me which model I want to load. It doesn't really matter. And then it starts creating our new training samples. So it's following the config value that I said earlier, which is just, so in this case, I usually have it set to 100, but in this case, since this is just for demonstration purposes, we're just going to do 5, so we're not waiting around forever. Because the 100s, depending on what else I'm doing on this computer, this will take between, I guess I'm not doing a lot at the moment because 7 seconds is pretty small a lot of the time. It's taking in the realm of like 30 to even a minute for some of the more complicated ones. That's also affected by how many iterations we're doing. So we're doing so how many like iterations of the Monte Carlo tree search we're doing. That's what this variable decides here, the training recursion count, which is set to 50, which is one of the relative. I only have 50 and 100 right now because anything more than that really did take just like so long. So after our training samples are created, we're creating our new challenger. So we're going to be fitting our policy and our value neural net, which happens quite fast. Even though you're using 1,000 samples, it happens almost instantaneously. So these are the results that we got. It's guessing the correct, or I mean, it's not guessing the correct move 56% of the time, but that's the accuracy that it's giving. It generates a probability vector and compares that to the probability vector given from the tree, and it is apparently 57% accurate. I'm not exactly sure how the math on that shakes out. And we can see that our ability to guess the type, whether it was a win or a loss or a tie, was up at 68%. And then our tournament starts. That's it. That's the whole process. Yeah, one thing that I'd like to talk about quickly is why sometimes you see champion dominance. So if you have a new champion, then that means that, so ideally that means that your new champion is a better neural net, it's going to be making better decisions, and it can take time to clear out kind of the bad training data that you have before, because if you have a better neural net now, then you're training your new neural nets on values generated by your previous generation. So in a way, your champion should be winning, should be expected to win, until such a time that like your training data starts to be replaced. So I have a training data cap, it holds on to 1,000 games. So there's kind of, if I'm doing cycles of 100 training sets, each time 10% of those games, those old games get replaced by the new games, and in 10 cycles, if you're not winning, then if your challenger is not learning, then that means that your project has probably reached maturity and is probably going to have trouble winning in the future. That's all I want to talk about in this video. If you have any questions, comments, leave them below, and I will read them and respond to them. Yeah, thanks for watching.